This video is going to be the start of chapter 14 on solutions. And in this picture we have an example of a brass instrument. And brass is actually a solid solution, so completely mixed together, of zinc and copper. This video is going to cover sections 14.1 and 14.2. So let's go over some general terms. We know that a solution is a homogeneous mixture of at least one solute and a solvent. So these words we reviewed in lab, but let's talk about again here. Our solute is going to be our substance being dissolved, and our solvent is our dissolving agent that usually is the most abundant substance in the mixture. And while these terms are associated with normally just liquids, we just gave an example of brass being an example of a solid, and we can also talk about mixtures of gases like air. So we have nitrogen, oxygen, argon, and carbon dioxide, and nitrogen would be the solvent as it's the largest portion of air, accumulating about 78%. So let's go over a review of these terms. Soda is a mixture of sugar and water, so our substance that's going to be our solute is going to be sugar. A solution is prepared by adding 25 milliliters of ethyl alcohol to 75 milliliters of water. Which substance is the solvent? We know that the solvent is always going to be in higher concentration, so we have B, our water. These are some other examples, and not that you need to memorize anything here, but just to give you an idea that we can constantly have different types of phases of matter dissolved in other solvents of different and sometimes the same phases. So we can think about soft drinks, carbonated beverages, salt water, ice cream. Lots of different things have dissolved phases in another phase. So solubility is related to that, and we're talking about the amount of substance that will dissolve in a given amount. So when we talk about potassium bromide, we know that 27 grams of potassium bromide can dissolve in 100 grams. And when two of these liquids or two compounds dissolve in one another, we're going to use the term miscible. And when two liquids do not dissolve, we're going to call them immiscible. So this mixture of oil and water is immiscible because we can see that they're constantly separating. So think about salad dressing. Our solubility rules are listed here. So when we're doing questions, while eventually you'll need to memorize these characteristics, while we're doing questions, keep this slide as a reference. You also received a solubility rules handout in lab that will accompany things we talk about in this chapter. And so on the left-hand side, you can see generally what ions are going to be soluble. On the right-hand side, those are some of our exceptions, and at the bottom are carbonates, phosphates, hydroxides, and sulfides. Most of those are insoluble except our ammonia ion and our group 1 metals. So keep that in mind and keep this slide as a reference for these next few questions. Let's go over these. So if we predict the solubility of barium sulfate, we know it would be insoluble because most sulfates are soluble except our barium one. Predict the solubility of sodium chloride. We know this is table salt, so this one's going to be soluble. Try and work on this one. Pause the video now. Silver nitrate, again, is going to be soluble. All of our nitrates are soluble. Silver hydroxide, we talked about hydroxides being insoluble, most of them. And our solubility of ammonium carbonate, we're going to say soluble, as all our ammonium salts are soluble. So you can sort of get some general ideas and trends based on the image I've showed earlier, as well as from the handout we've talked about in lab. Our other factors affecting solubility is we need to think that like dissolves like. So if we have a polar compound, we know it will also dissolve in other polar compounds and polar solvents. So if we dissolve ethanol in water, nonpolar compounds like carbon tetrachloride and hexanes, mostly carbon compounds, they're also going to dissolve each other. However, polar compounds such as water would not dissolve in nonpolar compounds such as carbon tetrachloride. So several ionic compounds dissolve in water and they end up separating due to their strong ion dipole forces, which we talked about in the last chapter. So we can see that our cation is going to be attracted to our negative oxygen atom, and our anion is attracted to the partially positive hydrogen atom. So you can sort of see here we have our green chlorine spheres being attracted to the insides of our water molecules. These are the last three terms for this section that I want you to know. We know that there are limits to how much solubility a compound can have at a given temperature. So when we're talking about saturated solutions, we have the maximum amount of dissolved solute in a solution. So here undissolved solutes and our dissolved solutes are going to be in equilibrium. Our unsaturated solutions are going to be less than the maximum, so lower amount, and our supersaturated solutions are greater than the maximum amount of dissolved solute. So for supersaturated, think you're making an iced tea from a powder mixture that you accidentally add too much powder and you can't get it to dissolve. This would be important because, as we mentioned with our definition, it has to do with a given temperature. So as you increase the temperature, we might end up increasing the solubility. So at a higher temperature, a supersaturated solution could become saturated. Why these solutions terms are important is that we know that if we were to take two solids together and put them in the same reaction vessel, we would see that there would be no reaction, or it would happen very, very slowly. When we end up dissolving both of the compounds in water, it allows ions to easier interact with each other and actually end up causing a reaction. So we can see here written out having our ions separating, giving us our silver chloride, which is insoluble. That's it for this video.